To pass the AEE exam's fluid mechanics section, mastering the pure equations is only the first step. The real challenge is understanding where that perfect theoretical math collides with physical fluid friction. To see how this works, we have to analyze two specific flow control devices, the orifice and the mouthpiece. An orifice is strictly defined as a simple geometric opening cut into the wall or base of a vessel, used to measure or restrict the rate of flow. A mouthpiece, however, is a very specific extension. It is a short pipe attached to that initial opening, and it is strictly defined as having a length equal to 2 to 3 times its own diameter. The central tension in calculating fluid discharge for these devices comes from the Bernoulli equation. Bernoulli relies on the assumption of a perfectly ideal fluid, meaning 100% of the potential energy converts cleanly into kinetic energy. But physical fluids behave differently. As water forces its way through a sharp metal opening, it tears away free boundaries. It experiences sudden contraction, abrupt expansion, and internal friction that creates chaotic downstream eddies. That turbulence bleeds energy from the system. To accurately calculate real-world discharge, we have to bridge the gap between theory and reality by applying empirical coefficients to correct the ideal equations. This flowchart maps the parameters to categorize orifices. They are categorized by shape, upstream edge profile, and whether they discharge freely or remain submerged. Pay close attention to the classification by size branch. This is where mathematical divergence begins. Size in this specific engineering context does not mean the absolute diameter of the hole. It is a strict mathematical threshold comparing the total pressure head of the fluid, H, against the vertical depth dimension of the opening, lowercase d. When the total fluid head is strictly greater than 5 times the depth of the hole, it is classified as a small orifice. At this substantial depth, pressure is uniform, allowing a constant velocity profile. However, for a large orifice, where head is less than 5 times the depth, the extreme pressure difference generates a slanted, uneven velocity profile. If you apply the constant velocity formula of a small orifice to a large orifice scenario, your discharge calculation will fail. The mathematics must strictly reflect the physical geometry. Looking at this orifice meter, we see why sudden restrictions bleed energy. As fluid approaches, trajectories bend inward, narrowing downstream. This critical pinch point, where velocity reaches its physical maximum, is the vena contracta. This creates a significant physical discrepancy. In your calculations, you cannot simply use the physical area of the cut hole as the flowing fluids area. The actual fluid stream is significantly narrower than the hole itself. To account for this physical reality, engineers rely on the core triad of hydraulic coefficients. The coefficient of contraction, Cc, handles the narrowing effect. The coefficient of velocity, Cv, tracks internal fluid friction, measuring the actual jet velocity against the theoretical ideal. It typically sits around 0.98. Multiplying these two ratios yields the overall coefficient of discharge, Cd. For a standard sharp-edged orifice, it consistently falls between 0.61 and 0.65. That total coefficient represents the efficiency tax the system pays simply for pushing fluid through a sudden geometric change. These specific coefficient values are not theoretical guesses. They are derived precisely through physical lab experiments, starting by determining the velocity coefficient. This schematic treats the exiting jet as a pure kinematics projectile problem. By selecting a target point, we apply base equations to measure horizontal travel and vertical drop. Because both directional paths share the exact same duration of flight, we can isolate and substitute the time variable. This links the planes, resulting in the experimental formula determining Cv using only the measured x and y coordinates and total head. Returning to the large rectangular orifice, simple constants break down. Because velocity increases with depth, we slice the cross-section into infinitesimally small horizontal differential strips, dH. To find the true discharge rate, we set up an integral capturing the flow through one singular strip, then sum it across the entire depth. Solving that calculus delivers the integrated expression for total large orifice discharge, multiplying 2/3 by the coefficient, width, square root of 2g, and the pressure head differences. This exact same integration logic is required for another tested scenario, calculating the precise time required to completely empty a draining tank. Remember the core proportionality rule. The total time to empty is directly proportional to the difference between the square roots of the initial starting head and the final head. While small, steady flow systems rely on empirical constants, large dynamic systems demand strict calculus to track ever-changing pressure heads. We've established how sudden restrictions destroy flow efficiency, but by deliberately modifying the boundary geometry outside the tank, we can significantly alter that behavior. This chart breaks down the taxonomy of mouthpieces: external cylindrical, internal, and convergent divergent. Taking the standard external cylindrical mouthpiece, adding this restrictive pipe to an orifice actually drastically increases the total coefficient of discharge to 0.855. Looking at the internal mechanism, we see why. As fluid enters the short pipe, it forms a vena contracta, briefly pulling away from the pipe walls. But because the pipe continues outward, the fluid jet eventually slows down and expands, completely touching and filling the internal diameter before it exits. As fluid expands outward to seal against the walls, it traps an empty pocket of space, creating a localized vacuum, a zone of absolute negative pressure. That trapped vacuum exerts a physical suction force backward, pulling additional fluid directly out of the tank, overcoming the minor friction of the pipe walls. A bare orifice relies entirely on the tank's static pressure to pull water out. A mouthpiece leverages its own expansion geometry to suck additional fluid out, generating a significantly higher total flow rate. At the macro level, selecting a flow device is an exercise in managing energy trade-offs. A tapered venturimeter maintains high energy with low head loss, but is expensive. An orifice meter is cheap, but you pay directly with massive head loss from chaotic turbulence. To navigate these calculations rapidly on the AEE exam, commit the critical constants and dependencies on this recall sheet to memory. Most importantly, the data confirms the central proportionality of flow. Velocity and total discharge scale with the square root of the head. Mastering fluid dynamics relies on visualizing physical behaviors. Success comes from seeing the flow separation, the vena contracta, and the localized vacuums that dictate real-world performance.